So, as you're going back to your table, you still do not need to log onto your computer. I just said to have it at your desk so we can be ready to go when we got there. Close your computer now. Appreciate you. Appreciate you. Alright. Perfect. So we're going to do a couple of different things today. We're going to be bouncing between a couple of activities, but in the midst of that, you're going to have some notes, okay? So let's go and take out a piece of paper for notes or notebook or whatever you wish. I'm going to be drawing some things. Those are not optional drawings. You have to draw the items or anything that I'm asking for you to draw, because actually some of the content we're talking about now is drawing intensive, right? So it's actually diagram intensive. So we have to be able to interpret diagrams or drawings as we go. So you can see the very first bit right here is why bonds form. So you can start with that. What I would be doing if I were reading, if I were taking this, I would be reading first to kind of get an idea of what this main topic is, and then just write down the details that are required. Not verbatim, because if you want these verbatim, I've already got basically all the PowerPoints up for the entire year, PDF forms, on my website. You can print that crap if you want to. If I wanted you to do that, I would not be doing this with you now. Okay? So after we take notes, we're going to be going to an activity on a computer and then back. Okay, so if I were to read this and pull out the main facts, I would see a couple of things. Simply, there's a reason for bonding. It's not just like, hey, you want an electron? Yeah, I think I want one today. There's no like just casual way that bonding is going to occur. It has a very specific reason. Because two independent atoms, like hydrogen and hydrogen, you guys saw this on the little interactive tutorial. The reason is hey, each of these hydrogens only have one electron. They're unstable. So once they get together and they share electrons, they have the duet, which we know duet is a comparable stability to the octet rule. So if you want to add that part there. Duet for small atoms, that would be things like hydrogen, lithium, beryllium, boron maybe, it's kind of a weird one. But we know that there's this stability that's achieved by bonding. So it can either bond by ionic bonding, where we're trading electrons. We can bond by covalent bonding, where we're sticking them in between us, and then we both can see them and kind of pretend they're ours. And then there's a weird metallic bonding, which kind of looks like this picture on the board. It's a blob, and that blob has floating cations, which are the core cations, which are the metal atom P cells, and these electrons that are floating around in a delocalized fashion. Now, they do this in a way that it kind of seemingly looks like they have octet. There's a lot of electrons floating around, but we won't really draw those too frequently. We're going to be drawing ionic and covalent more so. So stability is achieved. Energy lowering process means that they're stable. And if they're stable, they can stay in that orientation with the other ions or atoms in a very easy way. So the reason that we're achieving stability is because they have achieved octet, which is really stable electron configuration around their nucleus. So octet is a stable electron configuration. And who always has octet? What types of atoms? Noble gases. So they have that's why they are so stable. That means they are not reactive. So basically, once bonding has occurred, we just have to really put some energy into making these things react. Sodium by itself, like simply sodium with 11 electrons, like normal sodium, and chlorine by itself, actually I'll write this differently. Sodium with how many valence electrons? 1 valence electron, and chlorine with 7 valence electrons. Individually, these things are highly reactive, super reactive. Sodium is a metal that when it is exposed to water, it catches on fire. Chlorine is a gas that when exposed to you can like probably kill you. Chlorine gas, it's just a very hazardous thing. But when we put them together, we make a totally new compound by ionic bonding, which is safe to eat. Table salt, right? We put it on our French fries. So they become something very different once they are stable, meaning that we can actually, expose ourselves to them in everyday life and have no consequences. So independently, they're very different, but together they are a stable compound. Thumbs up if I can move on. Okay, so this is your kind of related to your chart, right? That's what I said, have your chart printed, because you might be adding a couple of details to it as we go. We're not rewriting this entire chart right now. So we already know that they create ions, right? Hence ionic. We already know they have electrostatic forces. We know their crystalline structures. They're super strong. They're actually the strongest of all bond types. You're kind of maybe checking this off on your checklist to make sure they're there. We already know that they're mainly room temperature or solid room temperature, high melting points and boiling points. And I say they're usually water soluble. What's the word soluble mean? Shut it out. Say it again? Dissolves, right? They will ionize and dissolve in water. The only other thing that I haven't indicated yet is how does the strength play into how does the structure play into the strength? So ionic bonds are incredibly strong. They're the electrostatic attraction, or the plus and negative attraction, that like magnetic little attraction, is super, super strong, bless you. But water can just like come up behind it, bring its little oxygen, oops, let's do the hydrogen this way. Hydrogen, oxygen, hydrogen, these are hydrogens. It can actually gang up on this. There's oxygen, hydrogen, and hydrogen. And it can actually rip sodium chloride, which is an ionic bond, apart. So though it's so strong, water has a very good attraction with it, with those ions, and it can rip them apart. So that's actually really important in our bodies. You guys know how your muscles work? Like how do you contract? How? That's the answer to everything, right? Come on, give me more. How do your muscles work? Anybody taking that in?
With your mind.
Next semester.
Next semester? So, tissues are contracting, but how does your brain tell your body to contract tissues?
It sends little messages to your nerves.
Okay, so what do your nerve signals look like?
They look like little spiky things. Right?
I mean, but what is a nerve signal? It's
Electricity.
Okay, it's actually electricity, electrical impulses, right? Okay, well, how does the electricity, like, automatically tell me to contract when it's not there? And then it's contracting when it's not there. Like, how is that happening? How do I control that? How about electricity explode?
I don't know.
I don't know. Okay, so that's what, here we go. So the reason that your body works that way is, I need a marker. I need this one. Okay. You have, those orange ones aren't really great. Okay, so it's called a neuromuscular junction. You've got your muscle, and you've got this like little cavity where your nerve comes in. It's sending electricity or electrical signals towards your muscle. But here there's called an ion channel. Sodium, potassium ion channel. That's one of them anyway. As the sodium comes into the muscle and the charge is actually built up as a positive charge, it tells your muscle to contract, and vice versa. When the charge goes to the other side of the channel of your muscle, it tells it to relax. It's just ions trading places, which creates a charge buildup, which your muscle's like, oh, I'm supposed to do this now, or oh, I'm supposed to do this now. So if ions can dissolve in our body, we would not be in good shape, because our nervous system wouldn't have any ability or way to communicate with our muscular system, and we'd be like a bag of water. That's what we're already just chemicals, right? But that's actually what's happening inside. So if stuff didn't dissolve in water, and if water wasn't one of the most prevalent liquids on our planet, we would have no ability to function. So there's actually some reasoning behind this. Anyway, the lattice energy is something we'll talk about later, so just put later on there, because that's an idea that's a little bit more than what I want to go into right now. All right, so for covalent, a couple more things I want you to make sure you add is they have a shape. So covalent molecules, you know, water, I kind of already drawn that already today, but it looks like this. That's what water looks like. Well, why in the heck does it have this little, like, bent shape? We call this bent. It's actually because these electrons, I'm drawing the electrons as dots right now, these electrons have what charge? Negative charge, right? And these right here, these are shared pairs, shared bonds or covalent bonds in terms of how we draw it here. So these are electrons too, technically. So what do electrons and electrons do to each other? Repel. So do you see that these electrons up here are kind of repelling this whole arm, and these electrons up here are repelling this whole arm? It's making it bent versus stay out flat. So the reasoning behind that is just because of electrons, and they repel each other. So we're going to start talking about these shapes eventually, but the whole shape theory comes from, or the shape prediction comes from the VSEPR theory. VSEPR, write that down. I'm having you add this to your charts, right? Okay, so VS, we call it VSEPR. That's just what we call it. Valence shell electron pair repulsion. Valence shell electron pair repulsion. Valence shell electron pair repulsion. Yes, it was in your reading guide. So that theory, the VSEPR theory, or the valence shell electron pair repulsion theory, will cause us to then identify different shapes that covalent molecules take on. We will get into that today. Another word I'm adding to your chart is the word volatile. Everybody raise your hand right now if you put deodorant on this morning. If you put deodorant on this morning. You put deodorant on? Yeah. All right, you smell it? Oh my gosh, cucumber melon is the best. Smell it? No. Okay. Cucumber melon? Whoa, okay. Just my opinion right now. All right. So, why can't you smell your deodorant?
Because it smells.
No, why? But why does it smell? Why does it? but that would be a solid, right? It's a solid stick, or whatever, right? Most people probably use a solid stick. You put the solid stick on you, but then you smell it. So what kind of state of matter is coming into your nose? I guess, but it was a solid, right? How did it turn gas? But it's volatile. The key word she started to talk about before she started this elaboration on deodorant, okay? So it's volatile. So what does volatile even mean? Okay. It can go. Well, it doesn't necessarily go straight from solid to gas, but it will vaporize easily. Thank the Lord, deodorant vaporizes easily, right? If we just be putting sticks of butter under our arm, we're like, oh yeah, I smell like butter. No, you don't. But it won't evaporate off your body heat, okay? So your bodies are hot. You're welcome. So your bodies are hot. They are warming up the deodorant, and that deodorant has volatile chemicals in it that kind of makes an odor, which makes you smell good. Versus making your little bacteria smells come out. You guys know it's just your bacteria that makes you smell that, right? Yeah. It's not you. It's your bacteria. So don't let me tell you that you smell that. It's your bacteria. They're basically just excreting poop and gas on you at all times, and they give you BO. Okay, a little biology in here today, okay? The only other thing I'll have here, add here, is that these are weaker than ionic bonds. Covalent bonds are weaker than ionic bonds. Okay? Right. Who drew this already on their charts? Or a version of this? Okay, so this is, don't go to this level of detail, but what you're seeing for an ionic structure is that this lattice is just a repeating layer of positive, negative, positive, negative, positive, negative. And if I was a good teacher, I'd have that structure.
And you must have it somewhere.
What a great teacher.
So, I'll let Grant start with this one. You can pass my ionic structure around. It's actually the crystal, right? That's obviously a blown up version of it. But it's a repeating layer that's stacked on top of each other of positive, negative, positive, negative. So if I were to throw that on the ground right now, Will, don't you do it. But if you were to throw that on the ground right now, what would we assume would happen? It would shatter, right? It would break. What's the word for that? What's the term that you maybe used in your chart that described the brittle? Okay, brittle means it would shatter. Okay, you can keep passing that around for now just so you can see it. Okay, moving on. So ionic, we're almost done with the ionic idea. We are going to be drawing them in their actual electron configuration style in a second. Ooh, before I move on, talk to the person next to you and tell them what you noticed about on a chart.
That's how many valence electrons except helium electron. Right is helium electron.
All right, back to me. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. Hush. Okay, Anthony, tell me what I'm trying to indicate to you about these red dots. Boom. Okay, so we dropped the mic. This is first a group, one valence electron for each one, right? A single dot is representing one electron. Grant, how many valence electrons are in group 6? 6 valence electrons, right? So oxygen, sulfur, and so forth have 6 dots around them. These are called Lewis dot structures. Who's ever seen these before? Okay, maybe in your book. Who saw them like in middle school? Okay, that's where I'm thinking a lot of you guys have maybe it's just a little bit of pre or prior knowledge. You can keep passing it around, but quietly, please. Blah, 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 please.
Oh, yeah.
The only weird thing about this is that helium, though it's in group 8, does not follow the rest of them in terms of their valence electrons, right? Because helium only has how many electrons? 2, okay? So technically, there are 2. Let me just move this. There are 2 electrons there. It's just the rest of them have 8 because they are in group 8. But helium is small, so it follows the duet rule, not the octet rule. Okie dokie? All right. So now we're going to start to use these pictures like this. Like we'll write the symbol, and then the dot will represent how many valence electrons they have. We'll use those to show how an ionic bond forms down. Okay? So I have an example before we draw our own. So as you're going through drawing dot structures, we just call them dot structures in general, and I will be writing some of this information down, okay? So as you're looking for dot structures, we call them also Lewis dot structures. We're going to write the symbol and the dots. And then we're going to do a little shimmying around of these electrons to make sure we're showing how they're actually exchanged. So take a minute there to read what I have first. Anybody else going to see this? You can see it, right? What's up? I would write on the bottom section. So my first 2 bullets here are just like your thought process. If you were to draw an ionic dot structure, first off you draw the dots with their symbols. So in my example here we have sodium. So this is like dot 1. We have sodium with 1 dot, because how many valence electrons does group 1 have? 1. We have separately chlorine with how many dots? 7. And that's going to be representing 7 valence electrons. So 1 valence electron, 7 valence electrons. And then the second thought you have to consider is, hey, somebody's got to have octet, or actually both of them have to have octet. How can I make that happen? So do I need to exchange electrons, or do I need to share electrons? There's got to be a meaning to the madness, right? There's a method to the madness. So I know off the bat this is ionic. But how would you guys know that? If I just saw sodium and chlorine. Don't look over here yet, right? Off the bat, how can you determine or predict this is ionic, Evan?
It's a metal and a non-metal.
Right, so we have a metal and a non-metal coming together, and if that's the case, immediately you should start transferring electrons because they need to form an ionic bond. They need to make ions. So sodium here has 1 valence electron. Okay, so this was our prediction of ionic by the nature of being metal and non-metal. Okay, sodium is one valence electron. We're going to circle that or draw an arrow with it, pointing like it's going towards chlorine. So this is what I mean kind of by drawing some diagrams. We have initial, we draw our arrow, and then at the end, we say now, so arrow yields, now sodium has a +1 charge. How? Loss in electrons, so loss in negative charge, so it's a negative, or it's a +1 charge. And then you must put brackets. You bracket the chlorine to say that now all of these surrounding chlorine are technically chlorines, which meaning chlorine gained 1 electron, so hence it has what charge? A -1 charge. Now, overall, we always consider these a collective entity. We say sodium and chlorine are now together forever until water breaks them apart. But this is forever together. So overall, +1 and -1 make what charge? Neutral. So that's what we say overall, this whole thing is neutral. Because you'll never find sodium without chlorine nearby. Sodium follows chlorine around like a lost puppy dog, okay? And that's why that's called an ionic bond, because they have technically attracted to one another and will not break that bond. Questions here? Thumbs up, can we move on? Okay, you guys are going to draw one yourself. Oh, hold on. I'll get to my little question here in a second. I want you guys to draw magnesium oxide. Similar story, magnesium oxide. Start for a second, okay? What's up?
So atoms will always bond if they can. Absolutely. Because instability.
Try magnesium oxide. All right, Jacob, how many valence electrons did you draw for magnesium? 2. Nicole, how many valence electrons did you draw for oxygen? And so Will just asked me, do I have to put them anywhere specific? No, I kind of just go around clockwise. You guys do whatever makes you happy, okay? Luke, what do I do with this?
Yeah,
What do you mean?
you transfer
Transfer, I like that word better. So you're transferring which ones?
the ones from magnesium,
Okay, so you're taking magnesium's 2 and you're transferring them to whom?
oxygen.
Oxygen. All right, Hannah, then what does that become? Okay, so oxygen with 8 valence electrons. And magnesium lost 2, so it has a +2 charge. What else do I need here? Good. Okay, so we have a +2 or -2. Overall, this is electrically neutral, because collectively it's neutral. We've shown the transition or the transfer of electrons so that we can see it's ionic. All right, who's good to move on? Yeah. This 2 right here? So I'm showing that this one gained 2 electrons. So if you gain 2 electrons, you want to show that with a -2 charge, because you gain 2 extra negatives. Okay, all right, talk to the person next to you about how the heck does this even relate to electronegativity? Okay, think back to what that is.
So that's one right now.
All right, back to me. 3, 2, 1. Izzy, what is the definition of electronegativity?
When
attraction to electrons are being shared in covalent.
Okay, so the attraction to electrons in a, I'm going to say, oh yeah, okay, I'll say a shared bond. Okay, so we have electrons and we are sharing them, right? Either, here's my scenario, okay, either if I have, let's just say I've got two cookies, okay? I can give 2 cookies to Savannah if she desperately wants them. She has to coerce me to do this, right? I'm not just willingly giving up cookies, no. So I can either actually literally give 2 cookies to Savannah, or I can say, all right, look, you're not getting both of them. All right, so we can share. Like I'll put them in here, and you can have part of it, whatever. Like just don't double dip or that kind of thing, okay? Or I can say, all right, I want to see like 1 cookie like next week, but I don't want to see it every week. I just want it to be here, so like if I need to see it, it's there. Okay, so I can totally give them up. We can share equally. Like she can have 1, I can have 1. Or I just want to see the cookie. I don't actually want it. You can hold it closer to you. And that's kind of the situation here. 3 options. So, totally taking cookies and giving them away would be like Ionic, giving up electrons. Equally sharing cookies would be something called a non-polar covalent bond. But we're sharing, it's just something with polarity. We're going to talk about that in a second. Or not sharing equally, where I gave her like the opportunity to have it more often than I had, then that would be called a polar covalent bond. Okay? So the polar covalent bond, polar bond, and ionic bond all stems from electronegativity, or the attraction to a shared pair of electrons. So who's more electronegative, magnesium or oxygen? Okay, everybody shout it out together.
Oxygen.
Oxygen is definitely more electronegative,
Yes.
right? You're doing your little fingers. So if oxygen is more electronegative, how do we indicate that here in our drawing? Luke.
Is it how many valence electrons it has?
In
the brackets.
the whole thing. No, give me the whole process. You're close though, Jasmine. How do I indicate that oxygen is more electronegative in my overall process here? Savannah's gonna help you out. Come back. Yeah.
Because instead of like giving all the electrons, you always want to take magnesium.
Right. It's not gonna give up these 6 electrons. It wants the electrons. It's gonna have a stronger attraction for them. So it kind of forces magnesium to give the electrons to itself, because this one's more electronegative. This one's less electronegative. So since magnesium here is less electronegative, does it really want its electrons that much? No, right? It is high on its own end, but oxygen's like higher this way and to the right. So this one's more electronegative, therefore it would transfer to oxygen, not vice versa. Okay, we're going to keep pulling this into this, the electronegativity, because everything builds basically from our latch unit. Draw this one now for me. So Marissa, what do you notice is happening in this kind of situation? Are we sharing electrons or are we donating electrons? Sharing, right? So what kind of bond would you consider this to be? Covalent. Okay. So if you're a covalent bond, you share electrons in the middle between 2 atoms. All right, Jasmine. Told you I would come back to you.
Oh.
Who do you think is more electronegative? Chlorine or chlorine? Come on. Right? So say it again. Okay. Chlorine, right? So they're both equally, they're the same atom, right? Neither can be more electronegative, it's the same atom. So if they're the same atom, they're equal in their desire to share or attract electrons.
So that's why we're sharing stuff.
Yeah. So chlorine's like, I'm not giving mine up, and this other one's like, I'm not giving mine up. They have to compromise. So then instead of giving up electrons, they must share. So these are the shared pair here in the middle. So we draw them collectively together with a shared, and I'm adding to my image, right? So to make sure that you're elaborating where you need to. Shared pair of electrons are sitting in the middle of them. We would actually, instead of drawing it as 2 dots in the middle, many times you guys will see me draw it like this. Dash, that dash is actually representing how many electrons being shared. 2 electrons. There's actually an electron here and an electron here. Okay, so this is how we'll likely draw it probably from here on out. All right, I want you guys to do the same thing for HCl. Make HCl. One dash equals 2 electrons. One dash. All right, Emma, get me started. Hydrogen has how many valence electrons? 1, okay. Anthony, chlorine has how many? 7. Everybody, oops. Everybody, what's going to happen? Okay, so these just kind of squish. This kind of squish, and then hydrogen's here, chlorine's here, but what's in the middle of them? Two dots, or I can draw what? A dash. This dash means 2 electrons, but chlorine still has the exterior, right, of which they already had. Say again? Which one, hydrogen? Because then hydrogen has no electrons, which is not satisfying the duet or the octet rule. So at this point, what it looks like is when I put a circle around hydrogen, and I put that circle there, including the shared pair, how many electrons does it look like hydrogen has? 2, which follows the duet rule, right? If I put a circle around chlorine here, including the shared pair, how many does it look like it has? 8. So we have duet and we have octet. So are they stable? Yes. And that's the goal. We always want to make sure that they're both stable. Okay? It's like a good relationship, right? You don't want somebody sucking the energy out of you. You need a stable relationship. Yeah. That was on our ionic situation. We would drop 1 electron and donate it to the other one. That was a metal and a non-metal. In this case, we're actually, what are you talking about? That's when we formed the ions. When we like dropped one and went back to noble gases, that's forming ions, which is ionic. Okay, good point. So she was just talking about how in the electron configurations, we would drop off 1 electron or gain more. That's still making ions. That's in our first scenario. Question?
All right, yeah. So will we not do an ionic one because there's no noble gas behind hydrogen?
Correct. Right. Okay, so we understand how to do our 2 basic drawings, okay? So I'm going to skip this for a second, and then I'll come right back to that. Actually, no, here we'll go with this. I want to spend some time, maybe 8 to 10 minutes here. Pull open your laptops for me. And so I said grab the laptop. Thank you. And I'll tell you what you're doing for me, okay? All right, when you're pulling out your laptops, you need to listen. When you're pulling out your laptops, you need to listen. So this is the cutest absolute comic that you could read regarding polarity. The polar bear and penguin comic. There are a couple questions there, but I think we can do this orally together. I just want you to quietly read my comic. So go to my homework webpage, okay? And just Google Jessica Enlow. It will pop up. Go to the homework webpage. I just put it under there so that you guys could easily access these documents. So what you're looking at under homework webpage, it says classwork, read polar bear article, and answer questions. Let's try to do this orally. So you're going to click on the read penguin polar bear. And it looks something like this. Looks like this, okay? So you're going to scroll down to the part where the comic begins, which would be down here. All right, so start with that. I'm putting some time on my timer so I can make sure you're getting what you need out of it. You can make it bigger when you have your PDF open. And if you want to share with the person next to you so you can get logged on, that might be helpful. Guys, I need some of you guys to still logging on, but I'm going reading. So while you're waiting, if you can see this. While you're waiting.
Oh my gosh, that's so fun.
Here's an option.
Yeah.
Miss Emma, did you make this? You have the ice for it.
Guys, stop getting so excited about my comic. I know. I already read it. Read it.
Is it supposed to be this?
Yeah, just put the ice for bottom. Gotta read it. Hoping for thoughts.
Continue reading by yourself, please.
Alright, come back to me now. Come back to me. I want to see where you are so far, okay? Halfway close your computer so I know that you're with me. Okay? And here we go. And this is what I would be adding to my notes. Okay? Add this as you go. They said something about a continuum. Continuum, right? Actually, I might pull it up for you guys. What is a continuum, by the way? Does anybody know that? Raise your hand. Something that's continuous, right? A continuum. So height, weight, bipolar, everything's a continuum. You go gradually increasing from one extreme to the other. So if I were to say I have a continuum of bond polarity, where do you guys want to start? It's on the board, by the way. Non-polar. So non-polar, meaning equally sharing electrons. I'm going to try to make this big so you guys can see what I'm writing. On what's the other extreme? Actually,
Polar.
hold on. Yeah, okay. The other end is what? Polar, potentially. What would be even more extreme than polar? Say again? Ionic. Like the epitome of, I just said it too? Thank you. So it was like, I'm not sharing anymore. I'm literally a full-on positive and a full-on negative. So you've got non-polar, I'm going to put covalent under here. So we understand that we're actually talking about covalent bonds here. And then all the way over here, we have ionic. And in ionic, we don't share electrons, period. We put a transfer of electrons up here to indicate that difference. So then what's in the middle? Polar bonds, right? Polar covalent bonds. So if this wasn't they shared equally situation over here on the left, and that over there is a like 100% transfer of electrons, what would you classify the middle to be? Sharing or not sharing? Sharing. Sharing equally or not equally? Not equally. Okay, so electrons shared unequally. So you guys might have a scenario you're thinking about there, maybe where you're sharing with somebody, or ice cream, I don't know, and they take more than they share, right? They were more greedy for the ice cream at that point in time. Or you have sandwich, you cut it in half, and they're like, can I have just a little another bite of yours? Right? They want more than their equal share. So that's actually what's happening within a bonding situation too. So the covalent side of things kind of blends into the ionic when we get to the point where the electronegativity differences are super, super drastically different. So over here, what do they say about electronegativity differences between two atoms that are bonding in a nonpolar covalent fashion? They're the same, right? So the same, and I'm just kind of making this a chart, a comic, I'm just kind of blending into a chart here, okay? So the same electronegativity. What about over here, in ionic world? What about their electronegativity? Like how different? Like super different. Like I'm so electronegative and you're not. I'm actually going to take your electron from you. There's no sharing ideas even at all. So this was vastly different. Actually, I just put a large difference. Use some big words here. Large electronegativity difference. So then what would be in the middle? Sort of different. So we put a medium electronegativity difference. Okay, so that's what we're looking at, is electronegativity and how does it play in the bonding. We're going to do a little bit more here, and we're going to draw some pictures with these. Stay with me. Some days you have heavy lecture days with Enlo. Today is one of those. Okay. So this little chart here, you guys probably can't see the numbers. Probably not. Right, hang out here. Make sure everybody gets one. Do not steal these, please. Do not steal these. Yeah. Yeah, come on. I'm trying to get my sleepy people. Alright guys, here, everybody get up and try to grab one from somebody. Get up. Take a picture first. Great. Here, Luke. Make sure we get one. Move on. Oh, what is that? Did I give you something wrong?
You gave me 4. I don't know who else needs them.
Raise
It's
your
so
hand if you don't
unorganized.
have one.
I gave you one.
I was so confused.
It's the same as all the rest of them.
Make sure everybody has one. Make sure everybody has one.
We need one.
I give you random things. Right, extras bring us Alright, did everybody get one?
Yes,
Awesome, thank you. Okay. Alright, come back to me.
Oh, wait.
No, that's fine, that works. They're slightly different copies. Okay, guys, ready? Thank you, come back to me. So, electronegativity is here. Look on your chart and tell me the electronegativity of fluorine. It's on the chart I just handed out, or my folks. Say again? 4.0, okay?
Oh, it's on the bottom.
So fluorine is the most electronegative element at 4.0. Let's look at hydrogen's electronegativity. 2.1, right? Kind of small. Let's look at sodium's 0.9, right? So you can definitely see the trend, this little hand trick. You can see it increasing across the table. But what do you notice about the noble gases?
There's 0.
Most of them are 0, right?
Yes.
These are 0, 0, 0. So are these going to interact in any way in bonding? No. So these will not bond. But then look at the lower noble gases. Do they have an electronegativity value?
Yeah.
Yes, okay, but they're still kind of small, so they don't really want to bond, but they're like, hey, like if I need to be in the bonding situation, I guess I can, because they have a large atom, and they can bond if they need to, yeah. No, these are my class sets, and usually I keep them colored or a laminated set, but please don't take these. You can take a picture if you want to. Take a picture. Okay, this is also on my website already, so it's not like a big deal if you don't, okay? And then look back up here for me. Looking back up here for me, okay? So that continuum you guys were designing over here, look. You said as this basically the same electronegativity. That would be a difference of 0 when you compare them. That is nonpolar covalent. You're good. But there is a little bit more to it. They can actually still have a really, really minor electronegativity difference, and they can still be a nonpolar covalent bond. Then you can have a little bit of a median difference, and you have a polar covalent bond. And if you have a pretty large difference, being like 1.7 and higher, it's going to be ionic. It's not going to be a covalent situation at all. You will always have this chart if you need to figure something out like that. Okay, we're going to worry about now why this matters. Okay, can I move on? Yeah. So we're going to be talking about the terminology shortly. Okay, so let's stay focused with me, guys. Yeah.
Why do some of the elements of like the bottom have just?
We don't know a lot about. So do you know that this is a not correct periodic table? This is an old periodic table. It's old, but it's because they don't have electronegativity values established yet. Okay. All right. So give me a thumbs up if this right here sounds like we just reviewed it. Does this look like something we just reviewed? Yes. Yep.
Yes.
Yep. What's the one word here that we haven't mentioned? Dipole, not diploid. Dipole. Okay, so the word dipole, guys, work with me here, okay? Dipole, you're going to put with the continuum under which category? Polar, okay? So dipole, here's how you draw a dipole moment. It's actually indicating, okay, this is an arrow. We draw a dipole moment like an arrow, and it's indicating where the electrons are being pushed towards. So in an unequal sharing situation, there's one area that's more negative. What would make it more negative? What subatomic particle would be there? More electrons are there. That's it. So there's more negative over here. We draw like a little lazy 8. We don't quite complete it. And we say there's more electrons on this side of the bond. And do you see this little hash mark right here? Kind of looks like a what sign? A plus, right? Which we would say a positive sign, right? So if something is has more electrons on one side, we put a partial, that's like a partial is what the symbol is, a sigma negative, and we put a partial positive here. And that's indicating the side that has less electrons. Right, go back to your reading. Go back to your laptops. You just won't be able to interact as much. Okay, that's how. All right, go to the second link. Second link that was under my website that you guys did not forget. Molecular polarity. Yes.
What?
On my computers.
Okay.
Okay, so what you're looking at is this. Give me a thumbs up if you're here. Okay, so it gives you a little background first. I do want you guys to write this on your notes, okay? So summarize like it says here, and then you're going to actually scroll down to the link. And I want you guys to play. Play like it says. Play and figure out how the simulation works. Play and figure out what the values mean. There are some questions here that I want you to start to attempt. You guys have about 15 minutes right now. Okay? Yeah, you need to, but we're not wasting time talking and moving about like this business. Okay? Yeah, that's fine. So you just want to interact. So look at it. Guys, if you stay in the chat, I'm gonna keep lecturing, or you can work. Okay, don't play with me. Jasmine, is that what you want? Okay. I'll recap. You are summarizing the paragraph. You are reading the instructions, and then you are playing with the simulation and kind of learn how to indicate polarity. Yeah, just do everything you said all the way.